So here's something you probably haven't thought about today, even though it's been with you every single second. Right now, wherever you are, electrons are moving, flowing through the wires in your walls, pulsing through the charging cable of your phone, racing along copper traces inside every device you own. The light in the room, if you still have one on, is powered by electrons that were pushed into motion at a power station maybe 100 miles away, shoved along by forces that most people never think about, traveling through a network so vast and so interconnected that it's arguably the largest machine ever built by human hands. And the wild thing is, nobody sees it. Nobody feels it. Electricity is invisible. You can't smell it. You can't taste it. You only know it's there because of what it does, because a light turns on, because a motor spins, because your phone buzzes in your pocket. And for most of human history, nobody had the faintest idea what it was. The story of how we figured it out, how we went from rubbing amber on cat fur and watching sparks to building a global electrical grid that powers civilization, is one of the greatest stories in all of science and engineering. And it's full of surprises, rivalries, spectacular failures, stubborn geniuses, and moments where one person's insight changed everything. That's what we're going to talk about tonight. Electricity. The whole beautiful, tangled, sometimes dangerous history of it. We're going to start thousands of years ago and work our way to the present. And we're going to take our time. If you drift off somewhere along the way, that's completely fine. The electrons will keep flowing, whether you're awake or not. And honestly, there's something kind of nice about falling asleep to the story of the force that keeps your world running. So settle in, get comfortable, and let's start where most great stories start, with someone noticing something strange and not being able to let it go. The ancient Greeks noticed it first, as far as we know. Around 600 BCE, a philosopher named Thales of Miletus, and Thales is one of those figures who shows up at the beginning of practically every branch of Western thought, the guy Aristotle called the founder of natural philosophy. Thales observed that when you rubbed a piece of amber with animal fur, the amber could attract small, light objects. Bits of straw, feathers, dust. It pulled them toward itself, as if by some invisible hand. Now, amber was a material the Greeks knew well. They used it for jewelry and decoration, traded it across the Mediterranean. Their word for amber was electron, and that word, that simple Greek noun for a pretty, golden, fossilized tree resin, is where we get everything. Electric, electron, electronics, electricity. The whole vocabulary of a force that shapes the modern world traces back to a Greek word for a stone you could rub on a cloth to make feathers dance. But here's the thing. Thales didn't understand what he was seeing. Nobody did. Not even close. For over 2,000 years, this phenomenon was a curiosity, a parlor trick, a mystery filed away alongside the equally puzzling behavior of lodestones, those naturally occurring iron-rich rocks that could attract pieces of iron without any rubbing at all. And for most of that time, people assumed these two phenomena were probably related. They both involved invisible attraction at a distance. They both seemed almost magical. Maybe they were the same thing? They weren't, as it turns out, but it would take centuries to sort that out. And in the meantime, the amber effect sat there, unexplained, a little thread dangling from the fabric of nature, waiting for someone to pull on it. Let's jump forward to the year 1600, because that's when someone finally took this seriously enough to do real, systematic work on it. His name was William Gilbert, and he was the personal physician to Queen Elizabeth I of England. Gilbert was a fascinating character, a doctor by profession, a scientist by obsession. He had very little patience for the armchair philosophers of his day who sat around debating what Aristotle had said instead of actually testing things. He was, in a lot of ways, a pioneer of the experimental method, the radical idea that if you want to know how nature works, you should go look, not just sit and think about what the ancient authorities said. That might sound obvious now, but in 1600, it was genuinely countercultural. Gilbert published a book that year called De Magnet, On the Magnet, and despite the title, this book did something revolutionary for our story. Gilbert carefully, methodically tested which materials could produce the amber effect, which substances, when rubbed, could attract light objects, and which couldn't. He tried everything he could get his hands on, and he discovered that it wasn't just amber. Glass could do it. Sulfur could do it. Wax, resin, various gemstones, a whole range of materials showed the effect. And he coined a term for this property. He called it the electric force, from that Greek word electron. So Gilbert is really the person who gave electricity its name. He also made a crucial distinction that had eluded people for 2 millennia. He demonstrated, through careful experiments, that the electric force and magnetism are different phenomena. They behave differently. They affect different materials. They follow different rules. Magnets attract iron and always have 2 poles, north and south. The electric force can attract anything light enough, and it requires rubbing to produce. That might seem obvious now, but in 1600, it was a genuinely important intellectual achievement. It meant electricity was its own thing, worthy of its own investigation, not just a footnote in the study of magnetism. But Gilbert couldn't explain what the electric force actually was. Nobody could. And for another century and a half, progress was slow, sporadic, and mostly accidental. People tinkered. They rubbed things together. They cataloged which materials did the trick and which didn't. But there was no theory, no framework, no real understanding of what was happening at a fundamental level. Then, in the mid-1600s, a German engineer named Otto von Guericke built something that changed the game. Von Guericke was the mayor of Magdeburg, which is a wonderful detail. This city mayor, who spent his spare time doing physics experiments. He's most famous for the Magdeburg hemispheres experiment, where he showed that 2 bronze hemispheres, fitted together and evacuated of air, couldn't be pulled apart by 2 teams of horses. That was about atmospheric pressure, and it was spectacular theater. But von Guericke also built the first machine for generating static electricity. It was a sulfur ball, about the size of a child's head, mounted on a shaft that could be turned by a crank. When you spun the ball and pressed your dry hand against it, it built up an electric charge. And you could draw sparks from it, real, visible, crackling sparks, jumping through the air. This was around 1663, and it was the first time anyone had built a device that could produce electricity on demand, rather than just rubbing a piece of amber with your fingers. Now, sparks got people excited, and I mean that in every sense. There's something visceral and dramatic about an electric spark, this tiny bolt of lightning jumping across a gap, and it drew attention to electrical research in a way that gently attracting feathers never had. Over the next several decades, experimenters across Europe built bigger and better electrostatic machines, cranking out larger sparks, and they started discovering all sorts of interesting things. In the 1720s and 1730s, an English dyer named Stephen Gray made a discovery that sounds simple but was actually profound. Gray showed that the electric force could be transmitted. You could charge up a glass tube at one end of a room and send that charge along a thread, a damp thread worked best, to the other end of the room, where it would attract a feather. But some threads worked and others didn't. Silk thread, for instance, blocked the transmission, Metal wire, on the other hand, carried it beautifully. The materials that carried charge, Gray called conductors. The ones that blocked it were insulators. And this distinction, this basic classification of materials into conductors and insulators, was one of the first genuinely useful pieces of understanding about electricity. It meant the electric force wasn't just stuck where you made it. It could travel, it could be directed, it could be sent somewhere. Gray's experiments became the talk of the learned societies in London, and he kept pushing the idea further. In one famous demonstration in 1730, he suspended a young boy from silk ropes, silk being an insulator, charged the boy's feet by touching them with a glass tube, and showed that the boy's face and hands could then attract small bits of brass leaf. The boy was, in effect, a human conductor, carrying charge from one end of his body to the other. It was theatrical, a bit absurd, and scientifically significant. Gray had shown that the human body itself was a conductor of electricity, and that charge wasn't something magical that only happened in amber and glass. It could flow through flesh and blood and metal and water, through anything that wasn't an insulator. He also showed that the shape of the conductor mattered less than the material. A long, thin wire and a short, fat rod would both carry charge, as long as they were made of the right stuff. These seem like simple observations now, but in the 1730s, each one was a genuine piece of new knowledge about how the universe works. A French scientist named Charles-François de Cisternay-Dufay took Gray's work further in the mid-1730s, discovering something that would prove crucial. Dufay found that there were two kinds of electrification, which he called vitreous and resinous. Glass, when rubbed, produced one kind, vitreous. Amber, or resin, when rubbed, produced the other, resinous. And here was the key observation. Objects charged with the same kind of electricity repelled each other, while objects charged with different kinds attracted. Two pieces of charged glass pushed apart. A piece of charged glass and a piece of charged amber pulled together. This was the first clear experimental evidence that electricity comes in two varieties, and that the attraction and repulsion of charged objects follows a pattern. Like repels like, opposites attract. It's a rule you probably know instinctively, but somebody had to discover it, and Dufay did. But the biggest leap of this era came in 1745, and it was discovered almost simultaneously by two people who didn't know about each other, which happens more often in science than you might expect. Ewald Georg von Kleist, a clergyman and amateur scientist in Pomerania, and Peter van Musschenbroek, a professor of physics at the University of Leiden in the Netherlands, independently discovered that you could store electric charge. The device they stumbled onto was beautifully simple: a glass jar, partially filled with water or lined with metal foil on the inside and outside. You touched the inner foil to a charged electrostatic machine, and the charge stayed in the jar. You could carry it across the room, set it down, come back hours later, and the charge was still there, waiting patiently. Touch the inner and outer foil simultaneously, and all that stored charge would release at once in a powerful spark, or, if you happened to be holding the jar in your bare hand, a powerful shock that could knock you off your feet. It became known as the Leyden jar, after Van Musschenbroek's university, and it was an absolute sensation across Europe. For the first time, people could accumulate large amounts of electric charge and release it all at once. The shocks were genuinely impressive. Van Musschenbroek himself, after receiving a severe jolt from his own device, reportedly wrote that he wouldn't take another one for the whole Kingdom of France. And people quickly turned the Leyden jar into a form of entertainment. They organized public demonstrations, spectacles really, where chains of soldiers or monks or willing volunteers held hands, and the first person in the chain touched a charged Leyden jar. The shock passed through the entire chain, and they'd all jump simultaneously. It was theater. It was hilarious. It was slightly dangerous, and very slowly, it was becoming science. This is where Benjamin Franklin enters the story, and honestly, Franklin is one of the most remarkable human beings in the entire history of electricity, or the history of anything, really. Franklin was already famous in the American colonies as a printer, publisher, civic leader, and inventor when he first encountered electrical demonstrations in the mid-1740s. A traveling lecturer named Archibald Spencer came through Philadelphia with an electricity show, sparks and shocks and Leyden jars, and Franklin was instantly captivated. He bought Spencer's entire set of equipment and threw himself into electrical experiments with the same manic intensity he brought to everything else. Now, Franklin's mind worked differently from most of the European researchers. They were mostly trained academics, working within established philosophical traditions. Franklin was a practical man, a self-educated polymath, a person who looked at a phenomenon and immediately asked, "What can we do with this?" And his contributions to electrical science were enormous. He proposed that electricity was a single fluid, not two separate fluids, as some European theorists believed. He introduced the convention of positive and negative to describe the two states of electrification, terms we still use today, though ironically, Franklin guessed wrong about which direction the fluid flowed. He thought it flowed from positive to negative. It actually goes the other way. Electrons flow from negative to positive, but by the time anyone figured that out, the convention was so firmly established that we just kept it. So, if you've ever been confused about why conventional current flows in the opposite direction from electron flow, you can blame Benjamin Franklin. He got the physics right, but picked the wrong direction. The Leyden jar was also the device that led to the first real theory of how electrical storage works. Franklin, studying Leyden jars in his Philadelphia laboratory, figured out that the charge wasn't actually stored in the water, as people first assumed. It was stored on the surfaces of the glass, on the metal foils lining the inside and outside. He demonstrated this by carefully disassembling a charged Leyden jar, removing the water, and showing that the glass itself retained the charge. This was a crucial insight, and it pointed toward something deeper about the nature of electrical storage. The Leyden jar was, in essence, what we now call a capacitor, a device that stores electrical energy in the electric field between two conductive surfaces separated by an insulating material. Every electronic device you own contains capacitors, and they all work on the same principle that Franklin identified in the 1740s. A capacitor in your smartphone and a Leyden jar in an 18th century laboratory are the same thing, differing only in scale and materials. But Franklin's most famous contribution, the one every schoolchild learns about, is his demonstration that lightning is electrical in nature, the famous kite experiment of 1752. And the real story is more interesting and more dangerous than the simplified version you probably heard. The popular image, Franklin standing in a thunderstorm, flying a kite with a key on the string, getting struck by lightning, is mostly wrong and would have been mostly fatal. What he actually did was fly a kite during an approaching thunderstorm. The kite was fitted with a pointed wire at the top, and the string was hemp, a good conductor when wet. At the bottom of the string, Franklin attached a metal key, and below the key, a silk ribbon, silk being an insulator, which he held to keep himself from being shocked. As the storm approached and the air became electrically charged, Franklin noticed the loose fibers on the hemp string standing up, repelling each other, which was a clear sign of electrification. When he brought his knuckle near the key, he got a spark. The ambient charge from the storm clouds had traveled down the string to the key. Lightning was the same stuff he'd been playing with in his lab, just a whole lot more of it. And here's the thing that separates Franklin the scientist from Franklin the engineer. He didn't just prove that lightning was electrical. He immediately figured out what to do about it. He invented the lightning rod, a simple, pointed metal rod mounted on the top of a building, connected by a wire to the ground. When lightning threatened, the charge would be drawn to the pointed rod and conducted harmlessly down the wire into the earth, rather than ripping through the building and setting it on fire. This was the very first practical application of electrical knowledge, and it saved countless buildings and lives. Churches, which were among the tallest buildings and stored gunpowder in their basements, a common practice in that era, had been particularly vulnerable. The lightning rod was adopted across Europe and America within years, and it made Franklin internationally famous. And the impact of the lightning rod was enormous. Before Franklin's invention, lightning strikes were one of the most common causes of catastrophic fires, especially in churches. This might seem odd. Why would churches be particularly vulnerable? 2 reasons. First, church steeples were often the tallest structures in a town, making them natural targets for lightning. Second, and more darkly, many churches stored gunpowder in their basements or vaults on behalf of the local government, because churches were considered safe, secure buildings. When lightning struck a church that happened to be sitting on a powder magazine, the results were devastating. In 1769, lightning struck the church of San Nazaro in Brescia, Italy, which was storing over 100 tons of gunpowder in its vaults. The resulting explosion killed about 3,000 people and destroyed 1/6 of the city. If the church had been fitted with a lightning rod, a technology that existed by then, those people would have lived. The tragedy at Brescia became a powerful argument for the adoption of lightning rods and resistance to the technology, which had been surprisingly strong in some quarters. Some religious leaders argued that lightning was an expression of divine will and shouldn't be deflected, largely crumbled after that. He was celebrated in Paris, honored by the Royal Society in London, and treated as living proof that useful knowledge could come from this strange new science of electricity. But for all his brilliance, Franklin still didn't know what electricity fundamentally was. He knew it behaved like a fluid. He knew it came in positive and negative varieties. He knew it could be stored and discharged and conducted and insulated. But the deeper question, what carries the charge? How does it actually move? Why do certain materials conduct and others don't? Remained completely mysterious. And the next great breakthrough in understanding electricity would come not from sparks and Leyden jars and kites in thunderstorms, but from a dead frog's leg twitching on a table in Bologna, Italy, in a laboratory where a doctor was doing something that had nothing to do with electricity at all. That doctor's name was Luigi Galvani, and what he noticed one afternoon in the late 1780s would set off one of the fiercest scientific rivalries of the 18th century and lead directly to the invention that truly launched the electrical age, a device that could produce a steady, continuous flow of electric current for the first time in human history. And the story of how it happened is one of the strangest and most consequential in all of science. Galvani was an anatomist, a professor of medicine at the University of Bologna, and he spent his days doing what anatomists did, dissecting animals, studying muscles and nerves, trying to understand how living bodies worked. Sometime around 1786, the exact date is a matter of some debate, he was working with a dissected frog, the kind of preparation anatomists used routinely, with the frog's legs separated from the body, but the nerves still attached, and he noticed something peculiar. When a metal scalpel happened to touch an exposed nerve while an electrostatic machine was sparking nearby, the frog's leg twitched. It kicked, as if the frog were still alive. Now, that alone was interesting, but not entirely unexpected. People had known for years that electrical shocks could make muscles contract. But Galvani kept experimenting, because that's what good scientists do. They notice something, and they can't leave it alone. And he found something much stranger. He hung dissected frog legs on brass hooks from an iron railing on his balcony, and the legs twitched. No electrostatic machine anywhere nearby, no Leyden jar, no thunderstorm, just two different metals, brass and iron, in contact with the wet tissue of the frog, and the muscles contracted. Something was generating electricity without any of the usual apparatus. Galvani concluded that the electricity was coming from the animal tissue itself, that living creatures produced their own form of electricity, which he called animal electricity. The frog was the battery, in his view. The metals were just conductors, passively carrying the charge that the biological tissue was producing. He published his results in 1791 in a famous paper, and the scientific world was fascinated. The idea of animal electricity was captivating. It suggested that the spark of life, the vital force that animators had always been looking for, might literally be electrical. It was a beautiful theory, and it was wrong. Or rather, it was wrong about where the electricity was coming from, while being profoundly right that electricity and biology are deeply connected. The debate between the animalists and the metallists wasn't just an academic squabble. It went to the heart of a question that had fascinated and troubled thinkers for centuries. What is the relationship between life and physical forces? Is there a special vital force that distinguishes living matter from dead matter, or is life just physics and chemistry all the way down? Galvani's animal electricity seemed to support the vitalists. Life produces its own unique form of energy, irreducible to mere physical forces. Volta's explanation was a blow to vitalism. The electricity wasn't biological at all, just an ordinary physical effect produced by the contact of different metals. The frog was incidental, a detector rather than a source. In the long run, Volta was right about where the current came from, but Galvani was right about something deeper, that biological systems do use electrical signals. Your neurons fire electrically. Your heart beats because of electrical impulses passing through cardiac muscle. The electroencephalogram, the electrocardiogram. These are technologies based on detecting the electrical activity of living tissue. Galvani's intuition was correct, even though his specific explanation was wrong. Science is sometimes like that. You can be right about the big picture and wrong about the details, or wrong about the big picture and right about one particular detail. But the electricity making those frog legs twitch wasn't coming from the frog. And the person who figured out the real explanation was Alessandro Volta, a professor of physics at the University of Pavia, about 200 kilometers northwest of Bologna. Volta was a different kind of thinker from Galvani. Where Galvani was a biologist, interested in life and living systems, Volta was a physicist, interested in fundamental forces and measurements. When Volta first read about Galvani's experiments, he was impressed and intrigued. But as he repeated the experiments himself, carefully varying the conditions, he began to suspect that the electricity wasn't coming from the frog at all. It was coming from the junction between the two different metals. The frog's leg was just a very sensitive detector, an exquisitely sensitive galvanometer, as we might say today, and its muscles were contracting in response to a tiny current produced by the contact of dissimilar metals through a moist conductor. The frog wasn't the source. The metals were. This set off one of the great scientific debates of the 1790s. Galvani and his supporters, the animalists, insisted on animal electricity. Volta and his supporters, the metallists, argued that it was contact electricity, produced by the junction of different metals. Papers flew back and forth. Experiments and counter-experiments were devised. Reputations were staked. The argument consumed the European scientific community for years, and it had a personal dimension too. Both men were proud, accomplished, and reluctant to concede. Galvani, in particular, took the criticism hard. He died in 1798, partly, some have speculated, from the stress of seeing his ideas challenged so publicly. But Volta proved his point in the most dramatic way possible. In 1800, he built a device that produced a steady electric current using nothing but metals and wet cardboard. No frog legs, no animal tissue of any kind, just a stack of alternating zinc and copper discs, separated by pieces of cardboard soaked in salt water or brine. Connect a wire from the bottom of the stack to the top, and you could feel a continuous shock. Not a single spark like a Leyden jar, not a momentary jolt that was over in an instant, but a sustained, steady flow of electricity. As long as the chemical reactions between the metals and the brine kept going, the current kept flowing. This was the voltaic pile, and it was the first true battery. And think about what that means for a second, because this is one of those pivots in history where everything changes. Before Volta, the only way to get electricity was friction, rubbing things together to build up static charge, or atmospheric electricity from thunderstorms, or the brief discharge of a Leyden jar. None of these were practical for sustained use. You couldn't power anything continuous with them. You couldn't do experiments that lasted more than a fraction of a second. The voltaic pile changed all of that, instantly. For the first time in history, scientists had a reliable, controllable, continuous source of electric current. It was like the difference between having a single match and having a furnace. The match lets you see for a moment. The furnace lets you work. Of it reached the rest of Europe, triggered something like a gold rush in experimental science. Everybody wanted one, and the batteries kept getting bigger and more powerful. Volta himself was invited to demonstrate his pile before Napoleon Bonaparte in Paris in 1801, and Napoleon was so impressed that he made Volta a count and awarded him a gold medal. The political implications weren't lost on anyone. A device that could produce a continuous, controllable flow of electrical force had obvious potential applications, from communication to medicine to warfare, even if nobody could quite see how to realize those applications yet. What they could see, immediately, was that the battery was a tool for new discoveries, and discoveries came flooding in. Volta announced his invention in a letter to the Royal Society of London in March 1800, and the response was immediate and explosive. Scientists across Europe began building their own voltaic piles within weeks, and new discoveries started pouring in almost immediately. One of the first and most important came from two English researchers, William Nicholson and Anthony Carlisle. They connected a voltaic pile to two wires dipped in water and watched as bubbles appeared. Hydrogen gas at one wire, oxygen gas at the other. They had broken water into its constituent elements using electricity. This was electrolysis, and it demonstrated something profound, that the chemical bonds holding molecules together are electrical in nature. The force holding a water molecule together is fundamentally the same kind of force as the one that makes a rubbed balloon stick to a wall. Chemistry and electricity are not separate departments of nature. They're aspects of the same underlying reality. The person who took that insight further than anyone else was Humphrey Davy. And Davy is worth spending a moment with, because he's a fascinating figure. Brilliant, charismatic, spectacularly talented, as both a scientist and a communicator. He was born in Penzance, Cornwall, apprenticed to a surgeon apothecary as a teenager, and largely self-taught in chemistry. He came to prominence at the Royal Institution in London, where his public lectures were so entertaining and so packed with dramatic demonstrations that they caused traffic jams on Albemarle Street. It became one of London's first one-way streets, just to manage the crowds showing up for Davy's talks. He was a showman as well as a scientist, and he was very, very good at both. Davy got his hands on increasingly powerful voltaic batteries, some of them truly enormous, made of hundreds of metal plates, and he used them to do chemistry that nobody had ever been able to do before. He discovered that if you pushed enough electrical force through a chemical compound, you could rip it apart into its component elements. And in 1807 and 1808, using massive batteries, Davy isolated a string of new chemical elements: potassium, sodium, calcium, barium, strontium, magnesium. Nobody had ever seen pure potassium or pure sodium before. These elements were so violently reactive, so desperately eager to combine with other things, that they'd never been found in elemental form in nature. Only the brute force of electricity could tear them free from their chemical bonds. When Davy first isolated potassium, a tiny, shining bead of metal that immediately burst into lavender flame when it touched water, he reportedly danced around the laboratory in ecstasy. His assistant later wrote that Davy's delight was boundless. Davy also built the first electric arc lamp, passing current from a massive battery between two charcoal electrodes and producing a brilliant, blindingly bright arc of light. This was the first electric light of any kind, decades before Edison. It was impractical for everyday use. It consumed battery power voraciously and burned through the charcoal electrodes, but as a demonstration, it was stunning. Here was light without fire, without combustion, powered by electricity alone. But Humphrey Davy did something else that turned out to be far more important than any of his own discoveries. In 1812, he hired a young laboratory assistant, a young man from a poor family in South London who'd been working as a bookbinder's apprentice since the age of 14. A young man with no formal education in science who had taught himself chemistry by reading the books he was supposed to be binding, and who had attended Davy's public lectures, taken meticulous notes, bound them into a beautiful volume, and sent them to Davy as a kind of job application. His name was Michael Faraday. And of all the things Humphrey Davy accomplished in his career, and he accomplished a great deal, there's a famous line, sometimes attributed to Davy himself, that his greatest discovery was Michael Faraday. Now, there's a sad footnote to the Davy-Faraday relationship that's worth telling, because it reveals something very human about the world of science. As Faraday's reputation grew, Davy became jealous. When Faraday was nominated for fellowship in the Royal Society in 1824, the highest honor in British science, Davy, who was then president of the Royal Society, actively opposed the nomination. Some historians believe Davy tried to claim that Faraday's early electromagnetic rotation experiments were actually based on ideas stolen from William Hyde Wollaston, another scientist. The accusation was baseless, and Faraday was elected to the Royal Society despite Davy's opposition, but the breach between mentor and protege never fully healed. Davy died in 1829, and Faraday, characteristically generous, always spoke of Davy with gratitude and respect, never publicly acknowledging the bitterness. It's a story as old as academia, the teacher who can't quite celebrate the student who surpasses him. But Faraday's graciousness in the face of it tells you something about his character. Faraday is, by almost any measure, one of the most important scientists who ever lived. And his story is extraordinary, partly because of where he started. Born in 1791 in Newington Butts, South London, the son of a blacksmith who was frequently too ill to work, Faraday grew up in poverty. He received only the most basic schooling, reading, writing, simple arithmetic, before being sent off to work. In the rigidly class-bound society of early 19th century England, a boy from Faraday's background had essentially no chance of becoming a scientist. That world belonged to gentlemen, to university-educated men with private incomes and social connections. Faraday had none of those things. What he had was a ferocious, almost desperate curiosity, an extraordinary ability to visualize physical processes in his mind, and an appetite for work that simply never quit. From his position as Davy's assistant at the Royal Institution, washing bottles, cleaning equipment, preparing demonstrations, Faraday absorbed everything. He watched, he listened, he experimented on his own whenever he could. And over the next several years, he rose from assistant to independent researcher to one of the leading scientists in Europe, entirely on the strength of his experimental genius. But the discovery that matters most for our story, the one that connects everything before it to everything that comes after, grew out of an observation made in 1820 by a Danish professor named Hans Christian Ørsted. And what Ørsted noticed during a classroom demonstration of all things was so unexpected and so far-reaching in its implications that when the news reached the rest of Europe, it set off a frenzy of experimentation that would ultimately give us the electric motor, the generator, the transformer, and the entire modern electrical power system. Ørsted was lecturing on electricity and magnetism at the University of Copenhagen in the spring of 1820. He had a wire on his demonstration table connected to a voltaic battery, carrying an electric current, and nearby, almost by accident, he had a magnetic compass, and as the current flowed through the wire, the compass needle moved. It swung away from north. When Ørsted reversed the current, the needle swung the other way. When he turned the current off entirely, it went back to pointing north, like always. Current on, needle deflects. Current off, needle returns. Current reversed, needle deflects the other direction. Now, think about what that means. For over 2,000 years, electricity and magnetism had been considered completely separate phenomena. William Gilbert himself had explicitly distinguished them back in 1600. They were studied by different people, described by different theories, filed in different mental categories. And here was Ørsted, watching a magnetic compass respond to an electric current. Electricity was creating magnetism. The two forces weren't separate at all. They were connected, deeply, fundamentally, intimately connected. A moving electric charge creates a magnetic field around itself. That's one of the most important discoveries in the history of science, and Ørsted stumbled onto it while setting up a classroom demo. Sometimes the universe gives you its biggest secrets when you're not even looking. And it's worth noting that the connection Ørsted discovered runs deep. It wasn't just that electric current happened to affect a compass. The relationship turned out to be fundamental, one of the deepest symmetries in nature. Electricity and magnetism aren't just connected. They're two faces of the same thing, two aspects of a single unified force. And the full understanding of that unity would take decades more to work out, requiring the combined efforts of Ampere, Faraday, and ultimately Maxwell. But Ørsted's compass needle, swinging in response to a current, was the first crack in the wall between two domains of physics that had been considered separate for millennia. Ørsted published his findings in July 1820 in a short paper written in Latin, and the news spread across Europe like wildfire. Scientists everywhere scrambled to understand this new connection, to measure it, to formalize it, to find out just how deep it went. And the person who moved fastest and dug deepest was André-Marie Ampère, a French mathematician and physicist who, within weeks of hearing about Ørsted's experiment, had produced a mathematical framework describing the relationship between electric currents and magnetic fields that is still used today. Ampère was a prodigy. He'd taught himself advanced mathematics as a child by reading through the entire encyclopédie in his father's library. He had a tragic personal life. His father was guillotined during the French Revolution when Ampère was 18, and his first wife died young, but his intellectual output was staggering. In the months following Ørsted's announcement, Ampère showed that not only does a current-carrying wire create a magnetic field, but two current-carrying wires exert forces on each other. If the currents flow in the same direction, the wires attract. If the currents flow in opposite directions, they repel. He formulated what we now call Ampère's law, which describes precisely how the magnetic field wraps around a current. And he proposed something even more radical, that all magnetism, including the magnetism of permanent magnets, is caused by tiny electric currents circulating within the material. That was an extraordinary leap, because it suggested that magnetism isn't a separate force at all. It's just what electricity does when it moves. The unit of electric current, the ampere, or amp, is named after him. And there's another name we should mention from this era, because his contribution is one you use every single day without thinking about it. Georg Simon Ohm, a German physicist and high school teacher, published a book in 1827 describing a remarkably simple relationship between voltage, current, and resistance. Voltage is the push, the force driving electrons through a wire. Current is the flow, the rate at which electrons actually move. Resistance is the opposition, how much the material fights back against the flow. And Ohm showed that these three quantities are related by an almost embarrassingly simple equation. Voltage equals current times resistance. V equals I times R. That's Ohm's law, and every electrical engineer in the world uses it dozens of times a day. It tells you that if you increase the voltage, more current flows. If you increase the resistance, less current flows. If you want to push a certain amount of current through a wire with a certain resistance, you need a specific voltage to do it. It's the most basic equation in all of electrical engineering, and it was published by a high school teacher who was largely ignored in his own lifetime. Ohm's colleagues dismissed his work as too simple, too obvious, and too mathematical. German academic culture in the 1820s was not especially receptive to physics done with equations. Ohm died in 1854 without having received the recognition he deserved, but we named the unit of electrical resistance after him. Every resistor, every wire, every component in every circuit you've ever used has its resistance measured in ohms. But Ampère thought in equations. Faraday thought in pictures. And it was Faraday's visual, tactile, almost sculptural way of thinking about forces that would produce the next great breakthrough. In 1821, inspired by Ørsted's discovery, Faraday built a simple but brilliant device, a wire hanging from a pivot over a cup of mercury, with a permanent magnet sticking up from the middle. When he ran current through the wire began to rotate continuously around the magnet, round and round, as long as the current flowed. This was the first electric motor. It was crude, just a dangling wire circling a magnet in a pool of mercury. But the principle was there. Electrical energy was being converted into continuous mechanical motion. The same principle, scaled up and refined, powers every electric motor on the planet today. But here's what really consumed Faraday for the next decade. Ørsted had proven that electricity creates magnetism. The natural question, the question that haunted Faraday, that kept him up at night, that he couldn't stop thinking about, was whether the reverse was also true. Can magnetism create electricity? If a current makes a magnetic field, shouldn't a magnetic field be able to make a current? Faraday was convinced it could, and he spent 10 years trying to prove it. 10 years of patient, meticulous experimentation. He tried every configuration he could think of. Magnets next to wires, magnets inside coils, coils next to coils. And for a decade, nothing worked. Other scientists tried and failed too. The problem was that everyone was looking for a static effect. They'd place a magnet next to a wire and wait for current to appear. It didn't. And then, on August 29, 1831, Faraday recorded the date precisely in his laboratory notebooks, which still survive. He finally cracked it. He wound 2 separate coils of wire around an iron ring, one coil connected to a battery and the other to a galvanometer, a sensitive current detector. When he connected the battery, the galvanometer needle kicked. When the current reached a steady state, the needle returned to 0. When he disconnected the battery, the needle kicked again, in the opposite direction. Current in the second coil appeared only when the current in the first coil was changing, not while it was steady, only during the moment of change, the moment of variation. This was electromagnetic induction, and I need you to understand just how important this is, because this single discovery is the foundation of the modern electrical world. What Faraday found was that a changing magnetic field creates an electric current, not a static magnetic field. A changing one. Move a magnet through a coil of wire and current flows. Stop the magnet and the current stops. Spin the magnet continuously and you get continuous current. It's the change that matters, the motion, the variation, and the implications are enormous. Before Faraday, the only way to produce electric current was chemical. You needed a voltaic battery, which consumed expensive zinc and copper and acid, and eventually, the chemicals were exhausted and the battery died. Faraday had just demonstrated that you could produce electricity from motion, from pure mechanical energy. Spin a magnet inside a coil of wire, or spin a coil of wire inside a magnetic field, and out comes electric current. You can power the spinning with a steam engine, a water wheel, a windmill, a turbine driven by falling water or expanding steam. Any source of mechanical force can be converted into electrical force. That's a generator. That's a dynamo. And that is the fundamental principle behind every power plant on Earth today. Every coal-fired station, every nuclear reactor, every hydroelectric dam, every wind turbine, every natural gas plant, they all work the same way at the core. Something spins a conductor through a magnetic field, and out comes electric current. Every single one. Faraday figured this out in 1831, with an iron ring and 2 coils of wire, in a basement laboratory at the Royal Institution in London, and the world was never the same. But Faraday gave us something else too. Something more abstract, but equally important. He introduced a concept that would transform how physicists think about forces. Instead of imagining electricity and magnetism as mysterious actions at a distance, charges somehow reaching across empty space to push and pull on each other, Faraday imagined that the space around any charged object or magnet was filled with something. Lines of force, he called them. Invisible threads of influence, radiating outward in all directions, filling the space, creating what we now call a field. The electric field, the magnetic field. The space around a magnet wasn't empty. It was alive with force, filled with a magnetic field that was just as real as the magnet itself. Faraday went even further with his field concept. He spent years conducting meticulous experiments on the relationships between electric fields, magnetic fields, and light. In 1845, he discovered the Faraday effect, that a magnetic field could rotate the plane of polarization of light passing through glass. Light, that most seemingly immaterial of phenomena, was being physically affected by magnetism. This was the first experimental evidence that light and electromagnetism were connected, a hint of the unification that Maxwell would complete 2 decades later. Faraday didn't have the mathematics to express what he'd found in equations, but he understood its significance. He wrote in his diary that he had at last succeeded in magnetizing and electrifying a ray of light and illuminating a magnetic line of force. He could feel the unity underlying all these phenomena: electricity, magnetism, light, even if he couldn't prove it mathematically. That was Maxwell's job, and Maxwell himself always credited Faraday as the true discoverer, the man who saw the physical reality that the equations merely described. Most of the mathematically trained physicists of Faraday's day dismissed this idea. They preferred action at a distance, which was mathematically well understood. But one person took Faraday's field idea very seriously, a young Scottish mathematical genius named James Clerk Maxwell. And what Maxwell did with Faraday's physical intuitions, translating them into rigorous mathematical language, would produce the most beautiful and powerful set of equations in all of physics, and unify electricity, magnetism, and light into a single, breathtaking framework. Maxwell was born in Edinburgh in 1831, the same year Faraday discovered electromagnetic induction, which is one of those lovely historical coincidences. He grew up on his family's estate in rural Galloway, showed extraordinary mathematical talent from childhood, and studied at Edinburgh and then Cambridge. He was, by all accounts, brilliant but gentle, a deeply thoughtful man who combined mathematical rigor with physical intuition in a way that few scientists before or since have managed. What Maxwell did over a series of papers from the late 1850s through the 1860s was take all the experimental laws of electricity and magnetism, Coulomb's law for the force between charges, Ampere's law for the magnetic field around a current, Faraday's law of electromagnetic induction, and several other relationships, and synthesize them into a unified mathematical framework. 4 equations. Just 4. That's all it took. 4 equations, now known as Maxwell's equations, that describe everything about how electric and magnetic fields behave, how they're created, how they change, and how they influence each other. But here's the thing that makes Maxwell's achievement genuinely staggering. When he assembled these equations and examined them as a system, he noticed something that none of the individual laws had suggested. He noticed that his equations predicted a new phenomenon. The equations said that a changing electric field would generate a magnetic field, and a changing magnetic field would generate an electric field. These 2 processes could feed each other. An oscillating electric field creating an oscillating magnetic field, creating an oscillating electric field, on and on, propagating through space like a wave. A self-sustaining ripple of intertwined electric and magnetic energy, requiring no wires, no charges, no medium, just empty space. And when Maxwell calculated the speed of this wave, when he plugged in the values of 2 electromagnetic constants that had been measured in laboratories, constants that described the strength of electric and magnetic forces, the number he got was about 310,000 kilometers per second, which was, within the margin of experimental error, exactly the measured speed of light. Maxwell himself wrote that the velocity was so nearly that of light that it seems we have strong reason to conclude that light itself is an electromagnetic disturbance. Light is an electromagnetic wave, the thing that lets you see, the thing that warms your face in the sun, the thing that creates rainbows and sunsets. It's a wave of oscillating electric and magnetic fields, traveling at 186,000 miles per second. And it's produced by the same fundamental forces that make a compass point north and a rubbed balloon stick to a wall. In one stroke, Maxwell had unified electricity, magnetism, and optics, three entire branches of physics, into a single, coherent theory. It is, by almost universal agreement among physicists, one of the greatest intellectual achievements in human history. And Maxwell's equations didn't just explain light, they predicted that there should be electromagnetic waves at every possible frequency, not just the narrow band our eyes happen to detect. There should be waves with much longer wavelengths than visible light, and waves with much shorter wavelengths. The entire electromagnetic spectrum, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, was implicit in Maxwell's four equations, waiting to be discovered. He predicted the existence of radio waves a full 2 decades before anyone detected them. Maxwell died in 1879, at just 48, of abdominal cancer, the same disease that had killed his mother at the same age. He never got to see the experimental confirmation of his greatest prediction. That confirmation came in 1887 from a young German physicist named Heinrich Hertz, who built an apparatus that generated and detected electromagnetic waves in a laboratory. Hertz's transmitter was a pair of metal rods with a spark gap connected to a high-voltage coil. When the spark fired, it created a rapidly oscillating electromagnetic disturbance that radiated outward as a wave. His receiver, across the room, was a simple loop of wire with its own tiny gap. When the invisible wave from the transmitter reached the receiver, it induced a current that produced a tiny answering spark. The wave had traveled through empty space, carrying energy from one place to another at the speed of light. Maxwell was right. Electromagnetic waves were real. When someone asked Hertz what his discoveries were good for, what practical use electromagnetic waves might have, he reportedly replied that they were no good whatsoever. He saw them as confirmation of a beautiful theory, not as technology. He couldn't have been more wrong, of course. Within a decade, Marconi was using electromagnetic waves to send telegraph signals without wires, and the age of wireless communication was born. Within 3 decades, radio broadcasting was a mass medium. Within 5 decades, television. Within 8 decades, cell phones. Within 10 decades, Wi-Fi, Bluetooth, satellite communication, GPS, radar, and 1,000 other technologies that work by sending and receiving electromagnetic waves. All of them are grandchildren of Maxwell's equations and great-grandchildren of Faraday's experiments with coils and magnets, and all of them confirm, every second of every day, what Maxwell predicted sitting alone with his equations, that light and radio waves and microwaves and X-rays are all the same thing, differing only in frequency. One unified phenomenon, discovered in pieces by a chain of brilliant minds stretching back to Thales and his amber, fully assembled by a Scottish mathematician who died too young to see how right he was. And within a decade, Guglielmo Marconi would use those waves to send the first wireless telegraph signals, and the entire age of radio communication would begin. But we're getting ahead of ourselves. Let's come back to the story of practical electricity, because while Maxwell and Hertz were working out the fundamental physics of electromagnetism, other people were working on a much more immediate question, one that would affect everyday life far more directly. The question was, how do you use electricity to light up a room? And more ambitiously, how do you use it to light up a city? And the answer to that question involves one of the most famous inventors in history, one of the most famous rivalries in the history of technology, and a battle that shaped how electricity is delivered to every home and business in the world to this day. The inventor is Thomas Edison. The rivalry is with Nikola Tesla and George Westinghouse, and the battle is known as the War of the Currents. But before we get to Edison and the light bulb, we should talk about the technology that first demonstrated to the general public that electricity could be useful in daily life, the electric telegraph. Because the telegraph is really the proof of concept for the electrical age, and it has a fascinating story of its own. The idea of using electricity for long-distance communication had been floating around since the mid-1700s, but turning it into a practical system took decades. The person who finally cracked it was Samuel Morse, a painter. That's right, a painter. Morse was a successful portrait artist in New York, and he got interested in electricity almost by accident during a ship voyage from Europe in 1832, when a fellow passenger demonstrated some electromagnetic experiments. Morse became obsessed with the idea of an electric telegraph and spent the next 5 years developing a working system, largely teaching himself electrical engineering in the process. Morse's system was elegant in its simplicity. A battery at one end pushed current through a long wire. At the other end, the current energized an electromagnet, a coil of wire wrapped around an iron core, producing a magnetic field that attracted a small lever, which made a clicking sound or pushed a pen against a moving strip of paper. By opening and closing the circuit in patterns, short and long pulses, dots and dashes, you could encode letters and numbers. Morse developed a code for this purpose, Morse code, assigning a specific pattern of dots and dashes to each letter. The letter E was a single dot. The letter T was a single dash. More complex letters had longer patterns. It was brilliantly designed, with the most common letters getting the shortest codes, minimizing transmission time. In 1844, Morse sent the first telegraph message over a wire strung between Washington, D.C. and Baltimore, Maryland, about 40 miles. The message, famously, was, "What hath God wrought?" And it was a demonstration that electricity could do something no other technology in human history had ever accomplished: transmit information faster than a person could physically travel. Before the telegraph, the speed of communication was the speed of a horse, or a ship, or at best, a semaphore signal, visible only to the next station down the line. After the telegraph, information moved at the speed of electricity, essentially instantaneous, over any distance you could string a wire. News that had taken days or weeks to travel now arrived in minutes. Stock prices, military dispatches, weather reports, family emergencies, all transmitted in real time. The telegraph collapsed distance in a way that changed commerce, journalism, warfare, and the rhythm of daily life so profoundly that historians sometimes call it the Victorian Internet. And then came the undersea cables, and this is one of those engineering stories that deserves a slow telling, because it's so audacious, so riddled with failure, and ultimately so triumphant. The first successful transatlantic telegraph cable was laid in 1858, connecting Ireland to Newfoundland. It worked for about 3 weeks, carrying messages including congratulations between Queen Victoria and President Buchanan, before the signal degraded and died. The insulation had failed, the voltage was too high, the cable design was flawed. The engineer in charge, Wildman Whitehouse, had used dangerously high voltages to try to push signals through the failing cable, probably damaging the insulation further. It was a spectacular public failure. Enormous money spent, enormous expectations raised, and then silence. But the cable's brief success had proven the concept was sound. A Scottish physicist named William Thomson, later Lord Kelvin, had warned before the laying that the cable design was inadequate and that the signaling methods were wrong. Thomson had worked out the mathematics of signal propagation through undersea cables and shown that you needed much more careful engineering, better insulation, lower voltages, more sensitive detectors, proper understanding of how electrical signals behave in very long conductors. The 1858 failure proved him right, and when the next attempt was made in 1866, Thomson's recommendations were followed. That cable worked, and it kept working, and by the 1870s and 1880s, a web of undersea cables connected the continents, carrying telegraph traffic and, later, telephone calls, creating the first global communications network. All of it powered by electricity, pushed through copper wires lying on the ocean floor, thousands of feet below the surface of the Atlantic. But let's start with the light bulb, because that's where Edison's story really takes off, and the history of the light bulb is more complicated and more interesting than most people realize. Edison didn't invent the light bulb. Let me just get that out of the way right now. The idea of producing light by passing electric current through a material that gets hot enough to glow, incandescence, had been around for decades. Humphrey Davy had demonstrated the electric arc back in 1809. In the 1840s and 1850s, various inventors had experimented with incandescent lamps, passing current through platinum strips or carbonized paper in glass enclosures. Warren de la Rue, Frederick de Molins, Joseph Swan in England, all had working incandescent lamps before Edison. Swan, in particular, had a lamp quite similar to Edison's, demonstrated publicly around the same time, leading to a patent dispute, eventually settled by merging their companies in England. So what did Edison actually do? Here's the thing, and this is key to understanding Edison's genius. Edison didn't just make a light bulb, he created a system. He thought about the light bulb not as an isolated object, but as one component of a complete electrical power distribution network. He asked the question that nobody else was asking with sufficient seriousness. How do you make electric lighting practical for millions of ordinary people? Not as a laboratory curiosity, not as a luxury for the wealthy, but as an actual replacement for the gas lamps that lit homes and streets and offices. And to answer that question, he had to invent not just a better bulb, but the entire infrastructure: generators, underground cables, junction boxes, fuses, meters, switches, insulation, everything needed to deliver electricity from a central station to hundreds of customers. Edison's approach to the bulb itself was characteristic of the man. He was relentless, systematic, and completely unromantic about the process. He tested material after material for the filament, the thin element inside the bulb that glows when current passes through it. Carbon, platinum, various metals, bamboo fibers, cotton thread, even hairs from a colleague's beard, according to some accounts. His laboratory in Menlo Park, New Jersey, first industrial research lab in history, really the prototype for every corporate R&D facility that came after, was staffed with dozens of skilled mechanics, glassblowers, machinists, and experimenters, all working under Edison's direction. Edison's Menlo Park laboratory deserves a closer look, because it really was something new in the world. Before Edison, invention was mostly a solo activity, a lone tinkerer in a workshop, or a gentleman scientist in a private laboratory. Edison created something closer to what we'd now call a startup. He assembled a team of specialists: Charles Batchelor, his chief experimenter; John Crucy, a master machinist from Switzerland; Francis Upton, a Princeton-trained mathematician who could handle the calculations Edison couldn't, and he organized their work toward specific goals, with deadlines and budgets and systematic testing protocols. The lab had a machine shop, a carpentry shop, a library, a glass-blowing room, chemical stores, and stockpiles of materials from around the world. Different metals, minerals, fabrics, fibers, anything that might prove useful for some experiment down the road. Edison called it his invention factory, and it was. Between 1876 and 1882, Menlo Park produced the phonograph, the practical incandescent light bulb, improvements to the telegraph and telephone, an electric power distribution system, and dozens of lesser but still profitable inventions. The model Edison created, dedicated, well-funded, team-based industrial research, would be adopted by every major technology company that followed, from GE and Bell Labs to Google and Apple. In October 1879, after more than a year of intensive effort, Edison and his team produced a lamp with a carbonized cotton thread filament that burned for about 13.5 hours. They improved rapidly. Within weeks, they had lamps lasting over 100 hours, and they eventually settled on carbonized bamboo filaments that lasted over 1,000 hours. On New Year's Eve 1879, Edison opened his Menlo Park laboratory for a public demonstration, and thousands of visitors poured in from New York City and beyond. The lab and the surrounding streets were lit by dozens of incandescent bulbs, all powered by a steam-driven generator. The effect was magical. Clean, steady, warm light, without the flickering and smoke and smell of gas lamps. The press went wild. Edison became the most famous inventor in the world overnight, the Wizard of Menlo Park, and public demand for electric lighting exploded. And then came the truly heroic engineering. On September 4th, 1882, Edison threw the switch at the Pearl Street station in Lower Manhattan, and electric light came to a section of New York City. The Pearl Street station was a marvel of integrated engineering. It housed 6 massive dynamos, each weighing about 27 tons, driven by steam engines burning coal. It supplied direct current at 110 volts to 85 customers within a roughly 1 square mile area, powering about 400 lamps. Underground copper cables carried the current through conduits beneath the streets. Meters tracked each customer's usage. Fuses protected against short circuits. It was a complete system, and it worked. But there was a fundamental problem with Edison's system, a physics-level limitation that he either failed to fully appreciate or stubbornly refused to acknowledge. And that problem was the nature of direct current itself. Direct current, DC, flows in one direction, like water through a pipe. Electrons go from the generator to the lamp and back, always the same way. It's simple, it's intuitive, and Edison loved it. But it has a devastating weakness when it comes to long-distance transmission. When current flows through a wire, some energy is lost as heat due to the wire's resistance. These resistive losses are proportional to the square of the current. Double the current, and you quadruple the losses. At Edison's operating voltage of 110 volts, you needed substantial current to deliver meaningful power, which meant substantial losses, which meant his system could only serve customers within about a mile of the generating station. Beyond that, so much energy was lost to heat that the lights at the far end would dim to uselessness. For a city like New York, this meant you'd need a power station roughly every square mile. Dozens of them, each burning coal, each needing real estate in one of the most expensive cities on Earth. It was technically feasible, but economically absurd. And here's the thing, Edison simply would not accept. There was a better way, a far better way. It used a different kind of current, exploited a different set of physics, and was championed by a brilliant, eccentric, tragically underappreciated engineer who had once worked for Edison himself and left in bitterness. His name was Nikola Tesla, and his idea was alternating current. Tesla's background is worth a longer look because it explains a lot about the kind of thinker he was. He was born in 1856 in Smiljan, a small village in the Austrian Empire, in what is now Croatia. His father was a Serbian Orthodox priest. His mother, though uneducated in the formal sense, was extraordinarily inventive. She made her own tools and mechanical devices for the household, and Tesla always credited her with his inventive temperament. As a child, Tesla experienced vivid visions and flashes of light, which he later learned to harness into a remarkable ability to visualize machinery in complete, three-dimensional detail inside his mind. He could conceive of a machine, build it mentally, run it in his imagination, identify where it would wear or break, and refine the design, all without sketching a single line on paper or building a physical prototype. This was so unlike Edison's trial-and-error approach that the two men almost couldn't comprehend each other's methods. Edison thought Tesla was impractical and too theoretical. Tesla thought Edison was wasteful and inelegant, once commenting that if Edison needed to find a needle in a haystack, he would examine every straw until he found it, whereas a little theory and calculation would have saved him 90% of the effort. Tesla studied engineering and physics in Graz, Austria, and it was there, during a lecture on direct current motors, that the idea for an AC motor first came to him. The professor was demonstrating a Gram dynamo, a DC motor that used brushes to maintain current flow, and the brushes were sparking badly. Tesla suggested that the motor could be designed without brushes, using alternating current instead. The professor told him it was impossible. Tesla spent the next several years thinking about the problem obsessively, and one evening in 1882, while walking in a park in Budapest, the solution came to him in a flash of insight that he later described in almost mystical terms. He saw the entire polyphase AC system, the motor, the generator, the transmission system, complete and working, rotating in his mind like a physical object he could reach out and touch. He drew the diagram of the motor in the dirt with a stick, and he knew it would work. Now, to understand why AC is so much better for power transmission, you need to understand what it is, and, more importantly, what it makes possible. So let's take a moment with that. Direct current flows in one direction. The electrons march one way, steadily. Alternating current reverses direction many times per second, 60 times per second in North America, 50 in much of the rest of the world. The electrons don't actually travel along the wire. They oscillate back and forth, jiggling in place, like people in a packed corridor swaying left and right. And your first reaction might be, well, why would you want your current going back and forth? Doesn't that seem less efficient? Less organized? What's the point? The point is transformers. And this is really the crux of the whole story. A transformer is a device that can change voltage levels, step it up or step it down, and it works only with alternating current. Here's how. You take an iron core and wrap two separate coils of wire around it, the primary coil and the secondary coil. When alternating current flows through the primary, it creates a constantly changing magnetic field in the iron core. That changing magnetic field, electromagnetic induction, Faraday's discovery, induces a voltage in the secondary coil. And here's the critical part. The ratio of the voltages equals the ratio of the number of turns in the two coils. If the secondary has 10 times as many turns as the primary, you get 10 times the voltage. If it has 1/10 as many turns, you get 1/10 the voltage. Simple, elegant, and incredibly useful. Here's why. Remember the transmission problem? Resistive losses depend on the current squared, not the voltage. And since power equals voltage times current, you can transmit the same amount of power at high voltage with low current or at low voltage with high current. The physics doesn't care which combination you use. The power delivered is the same, but the losses are dramatically different. If you step the voltage up by a factor of 100, you reduce the current by a factor of 100, and you reduce the transmission losses by a factor of 10,000. 10,000 times less energy wasted as heat in the wires. You can send power hundreds of miles instead of 1 mile. So the AC system works like this. Generate electricity at a moderate voltage, step it up to a very high voltage, tens of thousands or hundreds of thousands of volts, using a step-up transformer. Transmit it over long-distance high-voltage power lines at low current, losing very little energy. Then, near the customer, step it back down to a safe voltage, 120 or 240 volts, with a step-down transformer. The power arrives with most of its energy intact, over distances that would have been impossible with DC. Tesla had been thinking about alternating current systems since his student days in Europe. He arrived in the United States in 1884, carrying a letter of introduction to Edison and almost nothing else. He briefly worked for Edison, but the two men were fundamentally incompatible. Edison was a practical, hands-on, trial-and-error inventor. Tesla was a visionary and a theorist who could design complete electrical systems in his head, running them in his imagination, visualizing every detail before ever building a physical prototype. Edison tested 10,000 materials for a light bulb filament. Tesla would have worked out the optimal filament from first principles. They approached invention from opposite directions, and they clashed almost immediately. Tesla left after a dispute over money. He claimed Edison had promised him $50,000 for improving Edison's dynamos, and then reneged, saying the offer had been a joke. Whether that's precisely what happened is debated, but Tesla departed bitterly, and the two men never reconciled. What Tesla brought to the battle was the solution to the last major technical problem with AC, the motor. Transformers solved the transmission problem, but you also need motors, because an enormous proportion of electricity goes to turning things. Fans, pumps, compressors, conveyor belts, machine tools, elevators. DC motors were well understood and worked beautifully, straightforward designs that had been refined for decades. But building a practical AC motor was tricky, because the current keeps switching direction. How do you make a motor spin smoothly when the current driving it reverses 60 times a second? Tesla's answer was the polyphase AC induction motor, and it was a stroke of genuine genius. Instead of a single alternating current, you use multiple currents, typically 3, that are offset from each other in phase. Imagine 3 ocean waves, identical, but each one shifted by 1/3 of a wavelength from the others. When you feed these 3 currents into 3 sets of coils arranged around the inside of a cylindrical motor housing, they create a magnetic field that rotates smoothly, a spinning magnetic vortex. And a metal rotor sitting in the center of that field is dragged along by the rotating magnetism, spinning with it. No brushes, no sparking contacts, no commutator, just a smooth, elegant, nearly frictionless conversion of electrical energy to mechanical energy. Tesla's induction motor was simpler, more robust, more efficient, and cheaper to manufacture than any DC motor, and it's still the most common type of electric motor in the world today. The motor in your refrigerator, your washing machine, your air conditioner, your furnace fan. Overwhelmingly, these are variations on what Tesla patented in 1888. George Westinghouse, the Pittsburgh industrialist who had already made a fortune inventing the railroad air brake, recognized the superiority of AC immediately. He bought Tesla's patents, hired AC engineers, and began building an AC power system to compete directly with Edison's DC network. Westinghouse himself is an underrated figure in this story. Born in 1846 in Central Bridge, New York, he served briefly in the Civil War as a teenager, then went to work in his father's machine shop. He had a natural gift for engineering, and an even greater gift for recognizing important ideas when he saw them. His first major invention, the railroad air brake, was a direct response to a terrifying problem. Trains in the 1860s relied on brakemen stationed on every car, who had to manually turn brake wheels when the engineer whistled. The coordination was unreliable, and trains regularly failed to stop in time, causing wrecks and deaths. Westinghouse devised a system using compressed air, controlled from the locomotive, that could apply brakes on every car simultaneously. It was simple, it was reliable, and it saved thousands of lives. He patented it in 1869, at age 22, and built a company around it that made him wealthy. What matters for our story is the pattern. Westinghouse's instinct was always to identify a superior technology, acquire the patents, hire the best people, and build a system around it. He did it with air brakes, he did it with natural gas distribution, he pioneered safe methods for piping natural gas into homes, and he did it with alternating current. When he saw the European AC work and Tesla's polyphase system, he recognized immediately that this was better than Edison's DC, and he committed his company and his fortune to proving it. The confrontation with Edison wasn't something he sought, it was something Edison forced on him. Westinghouse's approach was to let the engineering speak for itself, while Edison fought with propaganda and fear. And what followed was one of the ugliest episodes in the history of American technology. Edison fought AC with every weapon he had, and some of those weapons were reprehensible. He funded public electrocutions of animals, dogs, cats, a horse, using alternating current, to demonstrate how dangerous it was. His associate, Harold Brown, staged these gruesome demonstrations, and while Edison maintained some public distance from the worst of them, he was quietly funding and coordinating the campaign. In 1890, the state of New York used alternating current to execute a convicted murderer named William Kemmler in the first electric chair, and Edison had lobbied behind the scenes to ensure AC was used, specifically so the public would associate alternating current with death. He reportedly tried to popularize the verb to Westinghouse as a synonym for electrocution. It was a smear campaign dressed up as public safety concern, and while the safety issues with high-voltage AC were real, Edison's motives were transparently financial and competitive. But the engineering spoke for itself, and it spoke loudly. The decisive moment came at the 1893 World's Columbian Exposition in Chicago, the Great World's Fair. It was an enormous event, 600 acres of exhibition halls and pavilions, and it needed to be lit with electricity. Both Edison and Westinghouse bid for the lighting contract. Westinghouse underbid Edison dramatically and won. He installed an AC system that powered over 100,000 incandescent lamps, and the fair was a blaze of electric light visible for miles. It worked flawlessly, efficiently, and safely. Millions of visitors saw the future, and it ran on alternating current. The knockout blow came at Niagara Falls. In 1893, the Niagara Falls Power Company awarded Westinghouse the contract to build a hydroelectric power station using Tesla's polyphase AC system. The generators were installed at the base of the falls, and in November 1896, AC power was transmitted over high-voltage lines to Buffalo, New York, 26 miles away. It worked perfectly. Cheap, clean hydroelectric power, generated by falling water, transmitted over distance with minimal losses, delivered to an entire city. The age of the modern electrical grid had begun. The Niagara Falls installation is worth savoring because it represented the convergence of every thread we've followed. The falls had been a source of wonder and a symbol of natural power for centuries. People had dreamed of harnessing that power since at least the 1700s. Early mills used water wheels directly, but they could only serve businesses literally at the edge of the falls. Electricity, specifically alternating current, changed everything. The generators at Niagara were enormous, each producing about 5,000 horsepower. They were driven by water diverted from above the falls through tunnels, spinning massive turbines. Tesla's polyphase AC system was used throughout. The electricity was stepped up to 11,000 volts for transmission to Buffalo, then stepped back down for local use. When the system came online in 1896, it was proof of concept on a grand scale. Clean, renewable hydroelectric power, generated miles from where it was consumed, delivered efficiently through AC transmission. It was the template for the modern electrical grid, and it's still in operation today, more than a century later, expanded and upgraded, but fundamentally the same system. Edison's own company, Edison General Electric, had already merged with another firm in 1892 to form General Electric, and within a few years, GE quietly adopted AC. The war was over. AC had won, completely and irreversibly. And every electrical outlet in your home is a testament to Tesla's vision. But Tesla's own story has a painful coda. Despite the world-changing importance of his inventions, Tesla died nearly penniless. He had sold his AC patents to Westinghouse for a relatively modest sum plus a royalty agreement. When Westinghouse later faced financial difficulties, Tesla tore up the royalty contract rather than see his friend and supporter go bankrupt. That single act of loyalty and generosity probably cost Tesla hundreds of millions of dollars in today's money. He spent his later years in a New York hotel room, increasingly isolated, increasingly eccentric, feeding pigeons in the park, and pursuing grandiose ideas. Wireless energy transmission, a death ray, a machine to photograph thoughts, that never materialized. He died on January 7, 1943, at age 86. He died alone. He died in debt. The man whose inventions light the world and power every appliance in your home. History has been kinder to Tesla's memory than his contemporaries were to his bank account. But it took a long time. Edison is still more famous. Ask any electrical engineer which of them mattered more, though, and you'll get a long, thoughtful pause. So let's talk about the world that AC built, because once the war of the currents was settled and the basic technology was in place, electricity spread across the industrialized world with a speed that's almost hard to comprehend. In 1880, there was essentially no electrical infrastructure anywhere. By 1930, just 50 years, most urban areas in the developed world had electric power. Streets were lit, factories hummed with electric motors, homes had refrigerators, radios, irons, toasters, vacuum cleaners. The transformation was breathtaking, and it changed everything, not just technology, society itself. Think about what electricity did to the home. Before electrification, your light after sunset came from candles, oil lamps, or gas fixtures. All of them dim, all of them flickering, all of them fire hazards. Thousands of people died every year in house fires caused by knocked-over candles and lamps. Electric light was brighter, steadier, and enormously safer. It extended the usable day. People could read in the evening without straining their eyes. Children could do homework. Factories could run night shifts. The entire concept of modern nightlife, restaurants and theaters and shopping districts blazing with illumination, is a product of electrification. Then came the appliances, the electric washing machine, replacing a full day of back-breaking manual labor with 45 minutes of loading, waiting, and unloading. The electric refrigerator, replacing the icebox that needed daily deliveries and couldn't keep food longer than a day or two. The electric iron, the electric stove, the vacuum cleaner. Historians have argued persuasively that household electrification did more to liberate women from the crushing burden of domestic labor than any social movement of the early 20th century. When a task that took 8 hours now takes 30 minutes, that frees enormous amounts of time and energy for everything else: education, careers, civic life, rest. And the transformation wasn't limited to homes and factories. Electricity remade cities themselves. Electric streetcars, trolleys, replaced horse-drawn carriages, and that single change reshaped urban geography. With horse-drawn transit, you could only build a city as large as a horse could reasonably pull a car, a few miles from center to edge. Electric streetcars could go faster and farther, which meant cities could spread outward. The suburbs, in the modern sense, are largely a product of electric transit. People could live miles from their workplaces and commute by trolley. Neighborhoods grew up along streetcar lines. Real estate values tracked the routes. The physical shape of the American city, spread out, with residential neighborhoods radiating from a commercial core along transit corridors, was determined by the electric streetcar before the automobile ever appeared. Electric elevators did something equally transformative. Before reliable electric elevators, buildings were limited to 5 or 6 stories, because nobody wanted to climb more stairs than that. Electric elevators removed that constraint entirely, and within a few decades, cities like New York and Chicago were reaching for the sky. The skyscraper is, quite literally, an electrical invention. Without electric elevators to move people up and down, without electric lighting to illuminate interior offices far from windows, without electric ventilation to keep air circulating, the modern skyscraper would be uninhabitable. The skyline of any great city is a monument to electricity. And then there's the social dimension that often gets overlooked. Electrification didn't arrive everywhere at the same time. American cities were largely electrified by the 1920s, but rural areas, home to nearly half the U.S. population, were mostly left in the dark. Private utility companies didn't want to build power lines to serve scattered farms miles apart. The economics didn't work. It cost the same amount to string wire to a farmhouse serving 1 family as to string wire on a city block serving 50. So rural America lived without electricity, without refrigeration, without electric light, without radio, without any of the labor-saving appliances that city dwellers took for granted, right up into the 1930s and 1940s. The change came through a government program, the Rural Electrification Administration, created in 1935 as part of Franklin Roosevelt's New Deal. The REA provided loans to rural electric cooperatives, organizations formed by farmers themselves, to build their own power lines and substations. It was one of the most transformative government programs in American history. By 1950, over 90% of American farms had electricity. The impact was immense and immediate. Farm families got refrigeration, electric pumps for water, electric milking machines, radio, and perhaps most importantly, electric light. The isolation of rural life was eased. Farmers' wives, who had been performing domestic labor under conditions that urban women had left behind a generation earlier, were suddenly freed by the same appliances. The gap between rural and urban life, which had been growing steadily since the Industrial Revolution, narrowed dramatically in a single generation because of wires on wooden poles. There's a famous photograph from this era that captures the moment perfectly. It shows a farm family gathered around a newly installed radio, listening to it for the first time. The expressions on their faces, wonder, delight, a kind of stunned gratitude, tell you everything about what electrification meant to people who had been living in the 19th century while their urban neighbors lived in the 20th. For these families, the arrival of electricity wasn't just a convenience. It was a connection to the wider world. Radio brought news, music, entertainment, weather forecasts, and market prices for crops. Electric light meant children could study after dark. Refrigeration meant food didn't spoil. Electric pumps meant running water inside the house instead of carrying buckets from a well. The gap in quality of life between a farm with electricity and a farm without was enormous, and the Rural Electrification Administration closed it in a single generation. By 1960, rural electrification in America was essentially complete. The grid reached everywhere. Industry was transformed just as radically. Before electric motors, factories were powered by one central steam engine, connected to every machine on the floor through an elaborate web of belts, pulleys, and overhead shafts. The entire layout of the factory was dictated by the need to stay close to that central power source. The belts were dangerous. Workers got caught in them with horrifying regularity. If the steam engine broke down, the entire factory stopped. Electric motors changed everything. Each machine could have its own motor, powered by a simple wire from the main supply. Factories could be reorganized for efficient workflow. Machines could start and stop independently. The shop floor became safer and vastly more productive. Historians estimate that the transition from steam to electric power roughly doubled manufacturing productivity, not because electricity was stronger, but because it freed factory designers to think rationally about production for the first time. But here's something most people never think about when they flip a switch, and it might be the most remarkable engineering achievement in this entire story. The electrical grid has to balance supply and demand in real time, every second. Electricity, unlike water or grain, can't be easily stored. There's no warehouse for electricity, no reservoir, no silo. It has to be generated at virtually the same instant it's consumed. When you turn on a light, somewhere a generator has to spin a tiny bit harder. When a factory shuts down for the night, generators throttle back. The grid is a continuous, dynamic, incredibly delicate balancing act. Millions of consumers turning things on and off unpredictably, and grid operators adjusting generation to match, second by second. If supply and demand fall out of balance, the frequency of the AC current, that 60 Hz hum, starts to change. Too much demand, generators slow, frequency drops. Too much supply, frequency rises. Everything on the grid is designed for that precise frequency. Even small deviations cause problems. Large deviations trigger cascading failures. Protective relays disconnect parts of the grid to save themselves, dumping load onto neighboring sections, which overloads them, which triggers more disconnections, and within minutes, the cascade can black out an entire region. That's what happened in the Northeast blackout of 2003. A software bug and some untrimmed trees in Ohio triggered a cascade that knocked out power to 55 million people across 8 states and part of Canada. The root cause was trivial. The consequences were continental. That's the hidden fragility beneath the extraordinary reliability of the grid. The grid that delivers this power to you is, by some measures, the most complex machine in existence. In the United States alone, it consists of over 7,000 power plants, over 160,000 miles of high-voltage transmission lines, and millions of miles of local distribution lines, serving over 150 million customers. It's not actually one grid. It's 3 interconnected grids: the Eastern Interconnection, the Western Interconnection, and the Texas Grid, which famously operates independently. Within each interconnection, every generator is synchronized to the same frequency, 60 Hz, and every generator responds to changes in load from every other part of the network. If a large power plant trips offline unexpectedly, every other generator on the interconnection feels the load change and adjusts, all within seconds. The whole thing is managed by a layer of sensors, computers, control rooms, and human operators working around the clock, making thousands of small adjustments every hour to keep the system in balance. And yet, for all its complexity, the electrical grid is remarkably reliable. In the developed world, the typical customer experiences electricity availability of about 99.97%, meaning power is available all but a few hours per year. That's extraordinary, especially considering that the system has essentially no storage. Every watt you consume is generated somewhere, at that moment, and delivered to you through a chain of equipment stretching back to a spinning turbine. The reliability of that chain, hour after hour, year after year, is one of the great unsung engineering achievements of modern civilization. You don't think about it because you don't have to. It just works. Until it doesn't, and then you realize how completely you depend on it. For light, for heat, for food preservation, for communication, for everything. Now, while the grid was expanding and transforming daily life, something quieter was happening in the world of electrical science. Engineers and physicists were learning to control electricity, not just for power, lighting and motors and heating, but for information. And this is where the story of electricity merges with the story of electronics, and eventually with the story of everything that defines the modern world. The distinction between electricity and electronics is like the distinction between plumbing and music. Electricity is about power, pushing current through wires to make things go. Electronics is about signal, using tiny, precisely controlled currents to represent, process, and transmit information. And the device that made electronics possible was the vacuum tube. It grew from an observation Edison made in 1883 while tinkering with his light bulbs. He noticed that if you sealed a second metal plate inside an evacuated bulb, near the glowing filament, a small current would flow through the vacuum from the filament to the plate, but only in one direction. He couldn't explain why. He patented it, labeled it the Edison effect, and moved on. It was one of the very few times Edison stumbled onto a fundamental physical phenomenon, and characteristically, he had no idea what to do with it. What was actually happening was thermionic emission. The hot filament was boiling electrons off its surface, and those electrons were crossing the vacuum and landing on the metal plate. But current could only flow from hot filament to cool plate, not the reverse, because the cool plate wasn't hot enough to emit electrons of its own. This one-way valve for current is called rectification, and in 1904, John Ambrose Fleming used the principle to build the first vacuum tube diode, a device for converting AC into DC, which was crucial for early radio receivers. But the real breakthrough came in 1906, when Lee DeForest added a third element, a fine mesh of wire called the grid, between the filament and the plate. He discovered that a small voltage on the grid could control a much larger current flowing from filament to plate. A tiny signal in, a big signal out. That's amplification. The device was called the triode, and it was the first electronic amplifier. It made long-distance telephone calls possible. It made radio broadcasting possible. It made television possible. And during World War II, it made the first electronic computers possible. Massive, room-filling machines like ENIAC, which used over 17,000 vacuum tubes and consumed as much power as dozens of houses. But vacuum tubes were fragile, expensive, power-hungry, heat-generating, and they burned out constantly. Building a computer from vacuum tubes was like building a cathedral from candles. Technically feasible, but you spent half your time replacing the ones that had burned out. The impact of the vacuum tube on the 20th century is hard to overstate. Before the vacuum tube, there was no way to amplify an electrical signal. You could transmit it, and it would get weaker as it went, until it faded to nothing. The tube changed that. It meant radio stations could broadcast signals powerful enough to reach millions of listeners. It meant telephone calls could span continents. The first coast-to-coast telephone call in the U.S., in 1915, was made possible by vacuum tube amplifiers spaced along the line. It meant the first practical radar systems could be built during World War II, giving the Allies a decisive advantage in detecting incoming aircraft and ships. And it meant that the first electronic computers could be constructed, not mechanical calculators with gears and levers, but true electronic machines that processed information at the speed of electricity rather than the speed of moving parts. ENIAC, completed in 1945 at the University of Pennsylvania, was the poster child for vacuum tube computing. It contained 17,468 vacuum tubes, weighed about 30 tons, occupied an entire basement, and consumed about 150 kilowatts of power, roughly the electrical consumption of a small neighborhood. Programming it involved physically reconnecting cables and flipping switches, a process that could take days for a single problem. And the tubes burned out constantly. On average, several tubes failed every day, and finding the dead tube among 17,000 working ones was itself a major task. The machine was so power-hungry that, according to local legend, when ENIAC was turned on, the lights in the surrounding neighborhood dimmed. Whether that's strictly true is debatable, but it captures the reality. Vacuum tube computing worked, but it was like trying to build a precision instrument out of candles. The transistor changed everything. Something better was needed, and it came from a deep understanding of materials that connects all the way back to the fundamentals we started with. The way electrons move through different substances, semiconductors. Materials like silicon and germanium that aren't good conductors and aren't good insulators, but sit right in between. Their special property is that their conductivity can be precisely controlled by adding tiny amounts of impurities, a process called doping. By clever arrangement of differently doped regions, you can create all the same electronic functions as vacuum tubes: rectification, amplification, switching. But in a device that's tiny, cheap, uses almost no power, generates almost no heat, and essentially never wears out. On December 23, 1947, at Bell Laboratories in Murray Hill, New Jersey, 3 physicists, William Shockley, John Bardeen, and Walter Brattain, demonstrated the first working transistor. It was a small, almost crude-looking device, a slab of germanium with 2 gold contacts pressed against its surface, but it could amplify an electrical signal just like a vacuum tube, in a package the size of a pencil eraser. No vacuum needed, no warm-up time, no fragile glass envelope, no burning out. The transistor is arguably the most important invention of the 20th century. It made possible the computer revolution, the internet, smartphones, satellite navigation, digital medicine, and essentially every technology that defines modern life. And at its heart, the transistor is just a very clever arrangement of semiconductor material that uses quantum mechanical properties of electrons in crystal lattices to control the flow of current with exquisite precision. It's electricity, tamed at the atomic scale. Within a decade, engineers figured out how to shrink transistors, and then how to put multiple transistors on a single chip of silicon. The integrated circuit, invented independently by Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor in 1958 and 1959. And then began the extraordinary exponential shrinking that Gordon Moore described in 1965, when he observed that the number of transistors on a chip was doubling roughly every 2 years. In 1971, Intel's first microprocessor had about 2,300 transistors. By the 2020s, Apple's latest chips contain over 100 billion. 100 billion tiny switches on a piece of silicon the size of your thumbnail, each one flipping on and off billions of times per second, each one controlling the flow of electrons, each one a descendant of that crude germanium slab Bardeen and Brattain built in a Bell Labs conference room on a December afternoon in 1947. And every one of those transistors works by controlling the flow of electrons, the same electrons that made Thales' amber attract feathers 3,000 years ago, the same fundamental force, understood now at a depth and precision that Thales, or Gilbert, or Franklin, or even Faraday could never have imagined. The electron doesn't care whether it's flowing through a copper wire to power Edison's light bulb, or oscillating in Tesla's polyphase motor, or being nudged through a silicon channel 5 nanometers wide in the latest smartphone chip. It obeys the same laws everywhere. Maxwell's equations govern the fields. Faraday's law turns the generators. Ohm's law describes the resistance. Coulomb's law governs the forces between charges. The same physics, from amber to microprocessors. One continuous, unbroken thread. And it's worth pausing to appreciate the sheer improbability of the chain that brought us here. An ancient Greek rubs amber on fur and notices a feather twitch. 2,000 years later, a queen's physician classifies the phenomenon. A century after that, a mayor builds a machine to make sparks. Then a printer in Philadelphia flies a kite in a thunderstorm. Then a doctor in Bologna sees a dead frog kick. Then an Italian count stacks zinc and copper discs. Then a blacksmith's son in London spins a magnet inside a coil of wire. Then a Scottish mathematician writes 4 equations that unify 3 branches of physics. Then a German physicist sends invisible waves across a room. Then a man in New Jersey strings wires under the streets of Manhattan. Then a Serbian immigrant dreams of a rotating magnetic field while walking in a park in Budapest. Then a cascade of engineers and scientists, each building on what came before, each adding one more piece, until the whole world is wired and humming. No one person could have done this. No one could have even imagined it from the start. The story of electricity is a relay race stretching across 3 millennia, where each runner picks up the baton in ignorance of what the final lap will look like. Thales had no idea he was starting something that would lead to smartphones. Franklin had no concept of a power grid. Even Faraday, for all his genius, couldn't have predicted the transistor. Each person simply noticed something fascinating, pulled on the thread, and passed what they found to the next person in line. That's how human knowledge works. Not as a grand plan, but as a chain of curiosity, one link at a time, stretching from amber to algorithms, from sparks to satellites, from a feather twitching in ancient Greece to the quiet hum of the grid in your walls tonight. And here you are, at the end of a story that spans 3,000 years, lying in the dark, maybe, with your phone nearby, or a charging cable plugged into the wall, or a fan humming softly in the background. Every one of those things is a product of this story. The outlet in your wall delivers alternating current because Tesla and Westinghouse won the war of the currents. The voltage is stepped down from high-voltage transmission lines by transformers that work because of the electromagnetic induction Faraday discovered in 1831. The electricity itself was generated at a power plant where something, burning gas, falling water, splitting atoms, or the wind, spins a turbine connected to a generator, converting mechanical energy into electrical energy using the exact same principle Faraday demonstrated with his iron ring and 2 coils of wire nearly 200 years ago. The fields propagating through your walls follow Maxwell's 4 beautiful equations, and whatever device you were using earlier today, every computation it performed, every image it displayed, every sound it played, was produced by billions of transistors, switching on and off, controlling electrons at the nanometer scale, exploiting quantum mechanics at the frontier of what we understand about matter itself. It's all one story, one long, continuous, astonishing story about an invisible force that humans noticed, puzzled over, feared, played with, fought about, and eventually learned to harness so completely that civilization now depends on it the way a body depends on blood. Electricity isn't just a useful technology. It's the nervous system of the modern world. It carries our information, powers our tools, lights our darkness, heats our food, connects us to each other across continents and oceans. And it flows silently, invisibly, through the walls around you right now, doing what it's done since the first electron moved, following the laws of nature, obeying the equations, indifferent to whether anyone is watching. The ancient Greeks had a word for it, because a piece of amber attracted a feather. And from that one small observation, this whole world grew. The lights, the motors, the generators, the grid, the computers, the phones, the satellites, the entire humming, buzzing, glowing infrastructure of modern life. All of it traced back, in a direct and unbroken line, to someone noticing something strange and not being able to let it go. There's something restful about that, if you think about it. The universe has these deep, elegant patterns, forces and fields and waves and particles, all governed by mathematical laws of extraordinary beauty, and they've been there all along, long before anyone discovered them, and they'll be there long after. The electrons don't need you to understand them to do their work. They'll keep flowing, keep spinning, keep obeying Maxwell and Faraday and Coulomb and Ohm, whether you're awake or asleep. So you can let go of the details now. Let the names and dates and equations drift. Let the story settle into the background, like the quiet hum of the electrical grid itself, always there, always running, always carrying energy from one place to another, reliably, invisibly, while the world sleeps. That hum is the sound of everything we talked about tonight. 3,000 years of curiosity and stubbornness and brilliance, all condensed into a quiet, steady, 60 hertz pulse in the walls around you. It's been there the whole time you've been listening. It'll be there when you wake up, and right now, it's keeping the world going while you rest. So let it. Close your eyes if you haven't already. Let the electrons do their work, and sleep.